Welcome to the Explainer. So pull up a chair and take a look at the blackboard here. We're doing a classic chalk talk today to uncover what is basically the secret language of calculus, sets and intervals. You know, if higher level math ever feels like totally foreign territory to you, you're absolutely not alone. But don't worry, we're going to decode the whole thing together right here on the board, stroke by stroke.
Now, what if I told you that math is just a giant room full of toy boxes? Sounds kind of crazy, right? It's a playful thought experiment, sure, but it's actually incredibly accurate. We're going to build up our understanding to the level of calculus by starting exactly like a 4-year-old learning to sort their toys. We're taking the really complex stuff and making it wonderfully simple.
Okay, let's take a quick look at the lesson plan written on the board. First, we'll open up the mathematical toy box. Second, we're combining and comparing sets. Third, we'll look at pieces of the number line. Fourth, a journey toward infinity. And finally, the secret to calculus. Let's just jump right in.
All right, Section 1, the mathematical toy box, focusing on the foundations of sets. For this part, I want you to literally imagine all of mathematics as just a series of different boxes, just waiting to be organized.
So the actual formal definition of a set, it's wonderfully straightforward. It's simply a box containing things that belong together. That's literally it. Think of it like a basket of apples and oranges. In math, we use these curly braces. You can think of them as the physical walls of our box. So if we write A equals curly bracket 1, 2, 3 curly bracket, that entire box is called set A. Simple, right? Now inside those curly walls, we have the individual toys, right? And we call those elements. An element is just something that lives inside the set. See that little curved E symbol on the board? That just means belongs to or is an element of. So 2 belongs to A. But if you cross that symbol out, it means it doesn't live there. So 5 does not belong to A. Oh, and notice the golden rule of naming here. Big capital letters are for the boxes themselves, and small letters are for the toys inside.
Okay, so what happens if you have a really small box that fits completely inside a bigger box? Well, we call that a subset. Take a look at the sets on the board. Set B has 1, 2, 3, 4, 5, and set A has 1, 3, 5. So everything in set A is also inside set B. Our tiny rule here is, if everything in the small box is also in the big box, it's a subset. We write that with that sideways U shape with a line under it. A is a subset of B.
But wait, what if your box has way too many toys? Like, what if you want to put all the odd numbers in a box? I mean, you can't write 1, 3, 5, 7, 9 forever. Mathematicians are, well, efficiently lazy. So we describe sets with a rule. Look at this. Curly bracket, 2n plus 1, a vertical line, n is an integer, close bracket. Step 1. That vertical line literally just means such that. Step 2. If n is 0, we plug it in and get 1. Step 3. If n is 1, we get 3. Step 4. If n is 2, we get 5. The result? We capture the infinite set of odd numbers perfectly in just one short line of chalk.
Moving right along to Section 2, combining and comparing sets, specifically looking at operations. Now that we know what these mathematical toy boxes actually are, what happens when we start playing with multiple boxes at the exact same time?
Let's compare two really key actions. On the left side of the board, we have union, represented by that big U symbol. Union basically means or. Imagine dumping everything from both boxes onto the floor into one massive collection. If a toy is in box A or box B, it's in the union. Now, on the right, we have intersection, which is the upside-down U. Intersection means and. Here, you are strictly looking for what is shared, what is inside box A and box B. Only the toys that exist in both boxes make the cut.
A really great way to visualize this is with Venn diagrams. You know, those overlapping bubbles you've probably seen a million times before. The union is literally everything shaded inside both bubbles. The entire thing. The intersection is just that tiny overlapping football shape right in the middle. But what if two kids have completely different toys, like cat toys versus dog toys? Those bubbles don't overlap at all, right? We call those disjoint sets. Their intersection is a box with absolutely nothing inside it, which we call the empty set, symbolized by that circle with a slash through it. All right, on to Section 3, pieces of the number line, also known as intervals. We're kind of shifting gears here. We're moving from these distinct, separate toys in a box to a continuous, unbroken piece of a road. It's a slight step up in complexity, but you're totally ready for it.
So, when we want a specific chunk of the number line, say, every single number between 2 and 5, and we mean everything, including 2.1, 2.5, 314,159. We use an interval. The absolute crucial point here is the brackets. Look at the table on the board. An open interval uses round parentheses. That means start at A and stop at B, but do not include the actual endpoints. Visually, we draw that as an open, empty circle. A closed interval, on the other hand, uses square brackets. That means we do include the endpoints, visualized by a solid, filled-in dot. And you can mix them up with a half-open interval, one square bracket, one parentheses. It's crazy how a simple change in punctuation literally changes the rules of the road.
Which brings us to Section 4, Journey Toward Infinity, the endless road. So what exactly happens when our piece of the road simply never ever stops?
Well, we have to define infinity, right? That classic sideways figure eight on the board. Now this brings us to probably the biggest misconception in all of math. Listen closely. Infinity is an endless direction on the number line. It is not an ordinary number. You absolutely cannot treat it like the number 5, or just add 3 to it in normal arithmetic. If we want to say every number greater than 3 forever, we write it as parentheses 3, comma, infinity, parentheses. And if we want the entire endless number line, absolutely all real numbers, that's simply negative infinity to positive infinity.
Let's connect all this together with solution sets. Sets and intervals give us a perfectly clean, really standardized way to write out our answers. Think about it. If an equation is x plus 2 equals 5, well, the only answer is 3. So the solution set is just a box containing the number 3. But if the problem is an inequality, like x is greater than 5, there are infinite answers, 6, 7, a million. So our solution set becomes the interval from 5 to infinity. It's just incredibly elegant.
And here we are, Section 5, the secret to calculus. Why learn sets? This is it! This is exactly why we spent our time today learning how to sort mathematical toys into boxes.
Let me just ask you this directly, and I've written it bold on the board. Why are sets and intervals so incredibly important in calculus? Why do math textbooks constantly insist on teaching you this stuff before you ever calculate a single derivative? Any guesses? It's because calculus is completely built on these blocks. Calculus is basically constantly asking, okay, which numbers are allowed? When you study a domain, you're asking what the set of allowed inputs is. Maybe it's the interval from 0 to infinity. When you study limits, you're zooming in and looking at tiny intervals close to a specific number. When you take a derivative, you're examining incredibly small shrinking intervals around x. And integration? Oh, integration is literally taking a closed interval from bracket A to bracket B and dividing it into millions of tiny pieces. The language of calculus literally is the language of intervals.
Okay, let's bring it all home. If you remember absolutely nothing else from today's Chalk Talk, remember these 3 big ideas written here. Number 1, a set is just a box, a collection of objects. Number 2, union means or and intersection means and. And number 3, intervals are just continuous pieces of the number line. Got it?
And this brings us to our final, empowering thought of the day. Sets tell us what numbers we have. Intervals tell us where those numbers live. Now that you fluently speak this secret language, now that you can sort the toys and draw the map, what will you build with them? Calculus is waiting for you. Thanks for joining me on this explainer, and remember, keep questioning everything.